This is an empty Godot project. By the end of this video, it's going to look like this. Fully working and functioning grid system. We're going to have layers like the fog of war. We're going to be able to move around with our pathfinding. We're going to have a fully functional grid system that you'd want in your game. But the great thing about it is that we're actually going to be able to make sense of everything that we see here, because we're going to build it ourselves. So let's get into it. Our empty project. So what are we actually going to try and do here before we write any lines of code? We're going to write a grid. The grid system really is going to be load-bearing infrastructure on a whole bunch of games. Every strategy game, the terrain, the pathfinding, the fog of war, the building placement, the unit movement, the resource gathering. All of this runs on top of a grid system. If the grid system is slow, everything is slow. If the grid API is awkward to work with, then every system that we touch within it is going to be awkward. So we're going to design this properly from day one. We're going to be fast. We're going to use like flat arrays for our integer coordinates instead of dictionary lookups. It's also going to be extensible. So we're going to be able to build a layer registry system on top, which will handle the fog of war, the influence maps, and any other kind of overlays that we want to write. Every episode, it's going to end with something on our screen that we can actually look at, right? No abstract theory. We're just going to see things. We're going to see things evolve as we build them, okay? So the first thing we're going to do is we're going to draw a grid. So we've got our test scene. Pop a script in. Yep, we'll call it test scene. Extend node 2D. In our function, we're going to draw. What do we want to draw? We want to draw a rectangle. So a rectangle needs a rectangle and a color. So the rect2 takes a position and a cell size. Position, let's say equals vector 2 and 10. Okay, we can put the position in there. Okay, the next thing is the cell size. So the cell size is always going to be a vector 2, and sure, we'll make it 1010 because that's a good size for a cell. So CS, now the color will be color dot Rebecca purple. See, right? Just like the current scene, we got a little tiny purple square in the corner. Fantastic. So we want to make a grid. Yeah, ready? We're going to have grid. So grid equals that. Height equals 40. Width equals 30. It's just so it's not a square, so we can see that we're doing a width now. So grid 4 y in height equals that for x in width and row that append a 0. Whatever, it doesn't really matter what we're doing here. Append row. Now we have a grid. Very nice. So down here we can we will have to calculate the position. So we will just do 4y in height for x in width. We'll do this. Okay. Problem is they'll all be drawn on top of each other at the moment because our position is not going to be calculated. So x and y. Now, of course, this won't work. We do have kind of a grid there, but it's not correct. And we'll show you how that's not correct because we'll have purple if x plus y modulo 2 equals 0. So we're going to do like a checkerboard color dot what's a good color? Aqua. So we should have purple and aqua squares, but actually we don't. They're all on top of each other. And that's because we've got a cell size of 10, but we're only going up by 1, right? So CS and CS and CS.y. So now we should have a nice little grid. Cool, little checkerboard grid. Okay. Okay, you say. The grid's easy. Well, it's not that easy. We're going to need a lot more infrastructure to support our grid system. So the first thing we're going to do is we're going to make a grid map. Grid. I'm going to call it the JES grid map. Okay. Plus name. JES grid. Of course, we're going to have a width. Of course, we're going to have a height. And wouldn't you believe it? We're going to have a cell height, cell size. 2. Beautiful. Now let's just line all these up so they look nice. Alright, so in the function, we're going to have an init, width, and a height, and a cell size. So, pretty easy. So the width equals W, the height equals H, so size equals CS. We'll get the coords soon. Don't have to worry about that. Alrighty. Index is expecting a closing bracket somewhere. What have we done? We didn't do that correctly. H and CS. Alrighty. So, yep. It's pretty straightforward. Let's make this for the grid. So over in our test scene, we can make a grid map instead of this whole grid stuff. So we just have grid, which is going to be just grid map. And now already, instead of doing all this, we're just going to create a new grid equals just grid map new. What was it, like 40 by 30, and we give it the vector to which will be the cell size, whatever. What was it, 10 by 10 or something? Yeah. 20 arguments for new. Oops, no. So now this is going to be grid dot height, but it's not happy for some reason. Yeah, it's all expected 0 but received 3. I feel like you didn't call it properly. Okay. Init function init. What's its problem? Ready. And everything just draws the same. So it's not too bad. But now we can see that this is going to be a problem. How do we know our position? And our size can just be the grid.cs cell size or something. Yeah. So we run that. We're still drawing our same grid. We've got to fix this. To fix this, we're going to have a new thing called a grid coordinate system. So let's get started with that. The grid coordinates, we're going to come through a script and we're going to call that GridCoord. Oops, we're not going to call it that. We're going to rename that. We're going to call it GridCoord. So this is going to be our universal coordinate type. It's just going to be a simple integer pair, x and y. You might be thinking, why are we going to make a class for this when we already have a vector 2 that can handle this? There, and it's built in. Yeah, that's true. You can use it. You can. But the reason why we're making this is so that when I look in the code, I'll see the grid coordinate and I'll know that we're working with grids. If I just see a vector 2i, it could be anything, you know, so it's not as clear. There's ambiguities there when we're looking through the code. And so we're going to be very deliberate in using grid coordinate so that we know we're in the grid space and we know what lives in the grid space and what lives in the world space. X equals px, y equals py. What's that problem? All right. Expected after the n equals 0. Sorry. Okay. All right. So pretty simple. The next thing we're gonna do is a very important method. It is our function to index. Okay. We're gonna have a grid width. It's gonna be an integer. And we're gonna return y times grid width plus x. So what are we doing here? What are we doing here? So previously we had an array that was like of grids that was like this. Each row, and each row had their array of all their cells, right? And we accessed it through X and Y. So that was okay, but not a very efficient way of storing data. What we want to use is a packed array. So what we do is we have a very long single dimensional array that has all of our grid cells in it. So we'll have, if it's a 5x5, 1, 2, 3, 4, 5 will be the first row, 1, 2, 3, 4, 5 will be the second row. And the way we access it is by, our width and our height. So, and plus whatever we're already accessing. So that way we can store all of our grid cells just as a flat array of floats instead of nesting into a dictionary. So that's basically what it is in Godot, is a dictionary. And why iterating the whole grid is as fast as a single for loop, right? Anyway, so now we need to continue building our grid coordinate system. We've got to have a few more little helpers here. We're not really going to use them right now, but we're going to use them later. So let's just whip them up right now. Static function from index int grid width int, and that's going to be a GridCoord. So we're going to just return a new GridCoord.new, and it's going to be our index, our grid width, index divided by our grid width. Yeah, what's its problem? Grid width. We need grid width, not grid width. Thank you very much. Let's make grid width as well. Yeah, why am I so dyslexic? Still saying grid width. Oh, width. Okay. Yep. Cool. I think that's all we need. So then the next thing we need is our const cardinal directions. So it's going to be just a little array of vector 2s. Now vector 2 this one, that'll be north, and then south, east, west. So 1 0 0 1 -1. Cool. So another one will be function direction, and direction vector to I, and that will return a grid chord, return grid chord new x plus x y plus direction dot y. Okay, we need an equals function, so equals yep, other grid chord return x equals other dot x and y equals other dot y. Function the Manhattan, so it's like the diagonal distance. Other grid chord, we need that path binding. And we just return the abc x minus other dot x and it's going to be plus absolute integer y minus other dot y. Cool. The next thing we need is just like the toString, so we can print it out in our debug. So return %d, %d, xy. Yeah, all right, that's pretty cool. Let's just make one more function there, and let's call that is valid. So is valid is going to be cool. It's just going to be a simple return x is bigger than 0 and y is also bigger than 0, because we can't have negative coordinates in our system. We always start at 0, 0. We can't have negatives. We're not going to support that. All right. GridCoord. So the next thing that we need is some mathematics. And this will make sense as we build it. So we're going to need a grid map class. Our class name shall be CoordMath. So the CoordMath is going to have a cell size. We're going to have the origin, so like where the cell is centered. That will also be a vector too. So when we emit, we're going to do cell size, and that's going to be a vector 2. And we're going to have the origin, which will be a vector 2. And we can just default it to a vector 2, 0. And we avoid because that's the constructor. Okay. Cell size is going to equal cell size. And origin. It's going to equal origin. All right, what is any unexpected? Could could not find the vector 2. That's true, because you should be a vector 2. Alright, sorry, that's the end there. Let's make a couple of little methods here that we're going to use literally 1,000 times in our function. So the world to cell. So our world position vector 2 is going to be our grid chord. Now our local position is going to be the world position minus the origin. And then we're also going to return the grid coordinates new. And it's going to be integer. We're going to floor the floats. And then we're going to go local.x divided by cell size.x, okay? And then we're going to do another int, and it's going to be a floor f. And it's going to be, fix that. It's going to be the local y divided by the cell's size.y. All right. And then we also need to do the opposite. So we need to go function cell to world, and that's going to be a coordinate. It's going to be a GridCoord, and that's going to be a vector 2, right? And what we return here is the origin plus the vector 2. So it's going to be chord x plus 0.5 times cell size dot x. And we're going to also do chord dot y plus half multiplied by the cell size dot y, right? So now you can notice that this has an error. Cannot find GridCoord. Okay, so you can see that we actually return the center of the cell here. So this one is the center of the cell, not the top left. This is the top left. Okay, now we do that because most of the time when we're interacting with a cell, like we're placing something on the cell or we're trying to click on it or whatever, we want the center of the cell. Yeah, and when we're drawing the cell, we actually need to draw it from the top corner, right? When we draw from the top corner. We don't draw from the center. So that's the thinking there. The last things we need to just add in is some boundary checks, right? We don't want to be getting out of bounds errors. So coordinate is a grid coordinate, and a grid W is an int, is an int, and a grid H is also an int. That of course will return a boolean. Expected end. Okay. Chord.x. I'm gonna go greater than and chord.y greater than or equal to 0 and chord.x w and y grid h. You're gonna do that a lot, right? Then we also need another one called the cardinal neighbor. There's going to be chord grid W is going to be an int, and grid H is also going to be an int. It's going to be an array of grid chords. Yeah. Okay. But equals grid chords equals that for the grid coordinates dot cardinal direction. So all the directions var n equals chord dot and the direction d. So if we're in the bounds, then of course we will do our W and our H, and we will out dot append that cell as a valid neighbor, and of course at the end we will just return n, no out. Alright, so it's got a few upset things here. Identify grid W is no good. It's no good. Okay. It'd be really nice if I could actually type grid properly instead of being dyslexic all the time. Out dot append n. Cannot find member append. Yep. Alrighty. That's the bounds check. Every neighbor lookup, so we avoid out of bounds. If you're like on the edge of the map or something, it's going to cause problems. Righty go. So, what are we doing? In our grid map, we've got to add a bit more stuff. We've got to actually add a coordinate system in here. We do CoordMath. So let's do that. Coords equals CoordMath and new CS. We're gonna need like the function to go. This is just like wrapper functions. And chord dot world to cell position. Why is it upset? Expected a thing. I didn't know. Too many of them. Yep. Okay. Function cell to world. Same thing. We take the coordinate. It will be a GridCoord, and we return the vector 2. Return coords. L2 world. Cool. Beautiful. And last but not least, our favorite function, the inbounds function. Coord grid coord is a boolean. Yes, it is. And we return chords. Return chords dot inbound. Inbound chord with. Cool. Very nice. I think we have everything covered. So back to our testing. Let's actually start using the grid map, which we are using, which is good. Do we have to change too much here? We don't have to change anything, I don't think. Oh, we have to change this because we don't want to do that. Let's let the okay, let's let the grid dot cells to world Chord CS. So that we just do this little bit just to put it in the middle. Otherwise, it would draw from 0, 0, like to negative. Negative. It'll put like the middle of the grid in the middle, which we don't want. But for our coordinates, we've just got to create a new one. Grid coordinate, new x and y. Cannot infer the type position because the value doesn't have. I think stuff up somewhere. World to cell to world, vector to. So okay, I don't know. It was just messing up. So we can actually run that now, and everything will draw perfectly. That's cool. That's about it. Really? That's our grid. We don't do too much with it, but you know, every system we build on top of this is going to use the same foundations that we build here to build upon a very flexible system. But let me quickly show you how the conversion works, the coordinate conversion works, all right? So we can do like an input, and then we can do the event input event. Void. Now we can go if the event is input mouse motion, then the coordinates. So this is where the value of this grid system comes in, right? Because now we can go world to cell position, right? So the mouse coordinates are going to get translated into what cell we are actually in. Okay, global. Classic, not spelling grid properly. Okay, global mouse position. Yep, so if we are inbound Chord, then of course we just print Chord, and we just get that. Do the redraw. Okay. Cannot infer the type of code. Grid world to cell. World to cell. Coolio. So now when we run small, we didn't do an inbounds on the. We need to do an inbounds. Up and downs. From the grid coordinates, we don't have. From the grid coordinates, we don't have any downs. What are we doing? We shouldn't have any bounds there. So from the grid, coordinate bounds. On the grid. Okay. I don't think that's correct, is it? I think what we actually want to do is check all the X's and Y's. Chord X, chord Y, grid W, grid W. I feel like that was right, actually. GridCoord doesn't have it. Yeah, that should be right. Now, when we go over, yeah, it translates for cool. So that's really cool. That's the end of episode 1. We've got a coordinate type, our world to grid conversion, and our first pixels on the screen. That's really cool. Really cool. In episode 2, we're going to build the things that make this whole framework special. The layer system, instead of one massive grid class, we're going to make this really cool layer system. We're going to build a registry system where we can register all the subsystems and we can just plug them in, and they'll handle their own data and logic on top of the grid. So the terrain, the pathfinder, and the fog of war, they're all going to be independent layers, and we're going to talk about each one for a clean and easy to use interface. So if you found this useful, subscribe, because we're going to be building something genuinely good here. It's going to be really cool. One episode at a time. Code's in the description. See you in episode 2.